Okay. Thanks for reminding me this. Yeah. Yeah. So you can see my screen.
Yes, yes.
Yeah. Sure. So yeah. So as I was saying, this is just going to be an overview of why we want to verify deep neural networks, how we intend to verify deep neural networks, and what are the challenges and how we try to overcome them in general in this field. So in some sense, it is going to be an overview of the kind of the flavor of things that you will see in this course. Okay. So firstly, let's talk a little bit about what a deep neural network is. So in general, you see what we're trying to do whenever we write a program is we're trying to uh, create a function with a certain some kind of a particular behavior, right? So the same thing is true with deep neural networks, except that we don't have a precise definition of what the behavior is, right? So for example, if you wanted to write a program to say identify a cat, or let's say uh, recognize a face, then doing that with traditional programming by defining exactly what you do with the pixel values and so on is going to be extremely difficult, because you'll have to go over all sorts of possibilities in the pixel values and so on. So machine learning and specifically deep neural networks are a very good way to achieve tasks or to perform tasks of this kind. So what you can do is essentially, or what a deep neural network is in an abstract sense, is essentially a parameterized model. So you have some sort of a structure where you have a bunch of parameters, and what the quote unquote training process does is that it will fix the values of those parameters so that the neural network will be approximately behave like uh, a particular function that you want to approximate with the network. So usually what we have is we have some training data, which is usually some input pair, input output pair. So x and y, we have a bunch of x and y, x being your input and y being your output. And the training process, somehow what it will do is it will fix the parameters theta of this deep neural network that we have, so that the deep neural network approximately produces y for all x, for all the x in the input. And the hope is that by giving it enough examples, you can actually define approximately a function that behaves intuitively like taking x to y by just by showing it some examples without having it to define it formally or precisely what exactly it needs to do. So I'm saying that the deep neural network is a parameterized model. So what is it exactly? What do the parameters do? How do you go from the parameters to actually calculating outputs from a given input, right? So for that, we need to know what like the structure of a deep neural network is. So what we have in a deep neural network are layers. So we have an input layer, and then some hidden layers, and then finally an output layer. What happens is your input values are passed into the input layer, and then they pass through an affine transform. So they are, you take your input values, you basically multiply them with some weights. So these arrows over here, these arrows basically represent multiplying with some weights. So over here, if you can see, there is this g over here. Can you guys see this? Is this too blurry?
No, I can see it. It's
Yeah.
visible.
Okay. So here we have taken g equal to 1000, let's say. So if we take g equal to 1000, we are, what we are doing is we are basically taking the value at this input. This represents an input. We are multiplying that with 1000, and then we are going over here. And similarly, we're taking the value over here. We are multiplying that with minus 1000, and then when we take the sum of these two, we get some value over here, right? And then finally to this sum, we'll add a bias. So we have basically weights along these arrows, which we will multiply with the input and then add all those values together. So if we write it like this, we have sigma wi xi, if your xi is our inputs, let's say. And then we have finally some bias, the bias that we add over here to get the next value, right? So we're doing this for many different output or intermediate neurons over here. These are called neurons, which is why we call this a deep neural network. These were originally inspired from biological neurons, although I don't know how good that analogy holds, but still we call them neurons. So what we do is we take the inputs and we pass multiply it with weights and add some biases. This multiplication with weights and addition of bias is basically doing an affine transform on your inputs, and then we get some values. Now what we do is we pass it through some nonlinear so-called activation functions, right? So if we just did affine transform over and over again, what we would get is just some linear thing. We don't want to just linearly transform our inputs. We want some nonlinearity in there so that they can make more complicated decisions. So we have some nonlinear activation function. Here the activation function we use is ReLU. So ReLU is basically, this ReLU function looks like this over here, where you put everything that is less than 0 to 0. So if your input of the ReLU is less than 0, so ReLU of x will be 0. Yeah. So hello.
Your screen has become blurry, I think.
Yeah, I
Yeah.
think somebody drew onto the thing. Okay, I'm sorry. Yeah, or I don't know why that happened. So I think Zoom lets you draw onto my screen as well. But if you do that, my screen becomes bloody. I don't know how that exactly works, to be honest, but it showed me that someone had drawn onto here. Yeah, was there any questions? Okay. So yeah, so what we have here is what we do is next is we pass it through this nonlinear activation function called ReLU. So what ReLU will do is if your input is less than 0, then ReLU of your x will be defined as 0. Otherwise, ReLU of x is x. Right? So this is what we do repeatedly. We have some affine transform on the input. We apply the affine transform to get some values. Then we pass it through the ReLU to get some new set of values inside this intermediate or hidden layer. Then we pass it through another affine transform and get another set of values. And then we pass it through ReLU again to get another set of values. So let's follow a few values in this network just to make sure that we understand what's going on. So for example, over here, if you see the input, there are two values. So x00 is 0.5, x01 is 0. So I've highlighted them here. What we're doing over here is then we're taking 1000 times 0.5 and minus 1000 times 0 and adding them together. So we get 500, and then we're adding 0 over here. So we get 500 here. Similarly, what we're doing over here is we're taking 1000 times 0.5 and minus 1000 times 0, and then adding minus 1 here. So that is 500 minus 1. So that gives us 499. Similarly, you get minus 500 here and minus 501. So you can check these calculations. Then when you pass it through ReLU, 500 remains 500, 499 remains 499 because both of them are greater than or equal to 0. Since minus 500 and minus 501 are negative, you get 0 over here. Finally, in this layer, what we do is we multiply this one over here. We multiply this one with 1 over here, and we multiply this one with minus 1 and then add 0 to it to get 1 over here. And similarly, we multiply 1 and minus 1 with 0 over here. So 0 and 0, and the output that we get is going to be 0. So our final output for the network is 1 at x20 and 0 at x21. So in this way, a neural network is basically takes your input and transforms it to get your output. So notice these weights and biases, this value g over here that we set to 1000 and 0, 0, minus 1, minus 1. These are what your training process will generate from you. So for now, we'll treat this training process as a black box. Later on, I'll just go into details of how you train a neural network at a high level, at least. But for now, let's imagine that somehow you have some oracle which, given your input-output pair, a bunch of input-output points, it will give you these weights so that the network closely approximates your desired function in some sense, whatever it means. So this is what yeah.
So like these, what's the difference between x0 and y00? Like so y00 is like before ReLU and after ReLU.
Yeah, exactly. So here in this particular diagram, the notation that I'm using is X, or okay, use a different color. X star star is, these are all before ReLU, or sorry, these are all after ReLU. Which includes, at the input layer. So right, and Y star star is just input to ReLU, also, or let's say before ReLU. So yeah, does that answer your question?
Yes, it does answer my question.
Yeah, okay. Yeah. Right, so the weights and biases, this theta that we had over here, this theta would be all the collection of these weights and all of these biases, and as I said, there is somehow some oracle which is the training process that finds out your good weights and biases. So we are not really focused on what this training process is exactly right now, although the deficiencies of this training process is what motivates us in some sense, but for now let's just consider that to be our black box, to be a black box. Sorry. So why do we want to verify deep neural networks, right? What do we mean by that, and why do we want to do it? Well, before we answer that, let's just talk a little bit about why we want to verify software at all, right? Because I mean, software is created with a certain goal in mind. Why not just, create it very carefully and then let it be, right? Well, you see, software is always, and this is not probably not very surprising to most of you, but software is really used in a number of safety critical systems. And there have been a number of accidents and tragedies, in fact, where a mistake in the software has led to loss of resources, and in some cases even loss of life. So some examples over here, some fairly morbid examples. There was this launch vehicle, this rocket called Ariane 5. In 1996, it was thankfully unmanned, but what happened was that around 30 to 47 seconds in flight, it flipped over and then disintegrated. So what was the cause behind this? Well, the cause behind this was an integer overflow. Right. So somewhere they were converting a float 64 value into an int 16 to feed into some actuator or something like that. And they had thought about that, okay, these integer values might, overflow. And so they had put in some protections in place for some of these variables. So I think they had a total of 7 variables that they were converting like this. And they had put in protections for 5 variables. But what happened was that an overflow occurred for the 2 variables that they didn't think about protecting. And that led to the loss of an entire rocket. And this is a fairly large rocket. Thankfully, no one was hurt, but I think around $7 billion were lost due to this crash. So as you can see, the stakes are quite high in certain safety critical systems. Some more examples, there was this Toyota unintended acceleration problem where there was some certain Toyota cars which had some small computers handling the engines. These are actually standard in most modern cars and airplanes. We have engine management systems, which are more often than not computerized. In 1992, so this was in 1996, even before that, in 1992, these EMS systems in the Toyota vehicles began to cause unintended acceleration, which is exactly as horrible as it sounds, right? It caused some loss of life, and there was some court cases, and they found that there was a number of stack overflow errors in their programs that they had not discovered. There was the Therac 25 was an radio therapy unit, and that was again computerized, and the dosage of the radiation that you would give to a particular patient would be controlled by this computer. And again, a bug in the computer, a very minor bug, caused an overdose of radiation to a number of patients in 1985. So these sort of computer bugs leading to very serious errors, where this is actually a very old problem. It's there back in 1985, right? And today we have not reduced the use of computers in safety critical places, but we have increased it. Like there's so many Tesla vehicles on the road, and they definitely, they run all sorts of machine learning driven computerized systems. And if there are a number of vehicles on the road which are driven by computers, you better have some guarantee that these computers are at least somewhat safe, otherwise all sorts of things will go wrong. So the main point about all of this is that all of these, they could be very easily fixed if somebody had found the bug, right? So if we have some framework for saying that, okay, whatever computer systems you have, it should satisfy such and such safety critical properties. And then when if you have a provably correct system to check these properties, then you can find such bugs before your product is deployed and it can actually cause some harm. So the point is that,
like it's a bit of a side question. Like, do these engine management systems are also in Indian cars as well, or like these are high-end cars?
No. Yeah, they are in all cars. In fact, I think so when these EMS systems, as far as I'm aware, what they do is they will fine-tune the timing between firing of the various spark plugs in your cylinders and such things so that you get better fuel efficiency and so on.
Okay.
So as far as I'm aware, they're in all cars. They're less common in lower end aircraft, but in all higher end or commercial aircraft, they're almost always there.
Okay.
So these EMS systems also produce your engine check lights. So,
oh, right.
Yeah, in modern or all modern cars, I think these produce your engine check lights and so on. So they have been very well standardized since 1992. So right now, I think the chance of an unintended acceleration happening is fairly low, but it goes to show that there should be and is a lot of standardization and standardized testing that is behind a number of these things.
This should be mandatory, or at least like software should be open source, man.
Yeah, no, this is very mandatory. Like, in fact, for aviation, any kind of avionics that you have,
about cars, like this is
even in cars, I think there are regulations in place that require things to be checked in that sense. Of course, there is
acceleration. This is about cars, right?
Yeah.
Yeah. So do they have some kind of regulation that checks their specifications or problems?
Yeah. There is such regulations, and usually these regulations are very stringent, and it's actually very expensive to do these checks, which is why you have very few number of EMS systems. Like different engine manufacturers actually use the same EMS systems because once it has been checked, then why not use the same one?
Okay.
Yeah, and of course there is a fairly good argument to be made for open source, but that is a discussion for another day.
Yeah.
So yeah, I think this doesn't need to be reiterated anymore. All software in safety critical systems need to be verified, and keyword is all software. The problem is today a bunch of this software, number of this software is some form of machine learning driven system, right? More often than not a deep neural network. There are other machine learning based systems, but more often than not, most modern systems that use machine learning use deep neural networks in one form or the other. And this is only increasing, right? So the number of places in which deep neural networks are very prevalent right now are small drones. And by the way, when I say small, they are still strong enough to lift a human being. So they're not, large aircraft in terms of commercial scale, but if they crash, there is some potential for a large amount of damage, especially if you have a large number of these drones operating, right? You have electric vehicles and smart vehicles. They have things like self-driving modes and such, which use DNNs for a number of key components. And the list of these things will only increase as, machine learning keeps on increasing in an exponential pace, right? And verification of DNNs is actually, very important, perhaps even more so than software, because DNNs are inherently, in some sense, error prone, right? So if you take any normal software, you have some very specific set of things that you want your software to do, and it's designed to do just that. And if it fails, it's because someone made a mistake somewhere. In DNNs, it's a little bit more difficult than that, because sometimes everything can go smoothly, your training goes well, but still the DNN just makes a mistake because it's approximate. And another thing is that DNNs are comparatively really easy to deploy right now, right? You don't need much to, like, you do need some amount of resources, but you do not need too much to train and deploy a DNN. And there is this a huge trend of training and deploying DNNs in a vast number of things, including safety critical domains. And so there has to be some sort of, well, even before we get to regulation or things like that, there have to be some sort of ways to check and verify DNNs, right? Which is what this field tries to ensure. We try to explore algorithms for checking and verifying DNNs against safety properties. So let's talk about a concrete example where a DNN was used in a safety critical system. So this is called the ACAS-XU system. So ACAS stands for Airborne Collision Avoidance System. It is, again, exactly as critical as it sounds. So this is a system that was used in autonomous vehicles, and it basically what it did was it would automatically, using a bunch of sensor data, try to detect, predict, and avoid imminent collisions. So this was not used for commercial or manned vehicles. There they had a different system that was called TCAS, as far as I remember. And the thing of the TCAS system is that there was some human intervention involved in that system. It was mostly just to produce a warning. But the ACAS system actually, will ask the aircraft, the unmanned aircraft, to change its course according to potential collision risk. So the original ACAS system was actually not something that did not use a DNN. So the original ACAS system used a lookup table, and that was around 2 GB in size, right? Then they switched to DNNs, which was this ACAS-XU system, and that reduced your size to 3 MB. So you can imagine there is a huge incentive to switching to DNN. However, now we have a verification problem. How do you verify that this DNN is, safe? And you see, the FAA has actually laid down some properties that need to be satisfied for this ACAS system for it to be considered safe. And one of the major things that have been done in the recent field is that we have been able to verify this ACAS-XU DNNs. It's actually a set of different DNNs for different input ranges. We have been able to verify this to satisfy the safety properties that have been specified by the FAA.
So they basically use DNNs here like compression kind of stuff.
Yeah, in some sense. Although the training process wasn't exactly, but in compressing the lookup tables, they used reinforcement learning to train this system.
Oh, okay.
Yeah. So there is a paper there, and I can link it to you. Although I haven't found an archive link for that. So yeah, I'll look it up and send it. So yeah, but they used RL to train this system, and the end result was, of course, the selling point was the compression factor, let's say. Yeah.
Okay.
Right. So what are the challenges in verifying DNNs, right? Or let's say, how is it different from normal program verification? So there are basically two main challenges. One is this property specification. With programs, you actually know you can very easily sort of specify certain properties that you think should be meaningful to verify, right? So for example, if you have a program that calculates factorial, it's very easy to state in very formal terms that, okay, this program calculates factorial. That is, if the input is n, then the output should be a number that is that has as factors all the things that are less than n, and that is the product of multiplying all of them. It's something like that, right? So you can specify that a program should calculate factorial very specifically, right? You can't do that with a DNN. How? Not always, at least. How do you specify that a DNN correctly identifies a cat? You can't do that. It's not very easy, at least. So that is one huge challenge. However, the identification of a cat might be an actually safety critical problem. Like if it's a self-driving car, it should not, it should try to stop if there's a cat on the road or something. Or if you replace the cat with another vehicle, then you see why this can be a really big problem. The other problem with verifying DNNs is that, the behavior for DNNs is always approximate. In fact, the desired behavior is approximate. We expect slight deviations, right? which is not the case with programs. In programs, if it's off by 1 bit, if your output is wrong by 1 bit, it is wrong. That's not the case with your DNNs, right? If it can be off by some tolerance, but then what is a good tolerance, right? How do you know what is a good safety margin to work with? So these are some of the challenges with respect to property specification, but still there are certain approaches via which we can circumvent this challenge, and there are still some properties that we can specify and that it is meaningful to check for DNNs. So these are the broad categories of these properties, and I'll give some specific examples for these. Okay, so by the way, if you have any question, do interrupt me. I think that I should have said that, but yeah, hope that is implicit. Yeah, so for in terms of safety, see, whenever you use anything or any system in a safety critical environment, you don't need a complete functional sense of correctness. By functional correctness, I mean, as in a factorial program calculates a factorial, right? So you know that the program as a function behaves like a factorial calculating machine. So you don't need to have this functional sense of correct behavior always for safety critical systems, right? You just need some bound of, whatever your system is, it should not leave this safe region, right? It should not enter into any unsafe region of behavior. So that is often a good enough or at least a very meaningful first step towards verifying things for safety critical systems. So for example, for the ACAS system or even for the ACAS XU system, let's say, then the DNN should not provide an instruction to go left. Okay. Highlight failed. Sorry. Yeah. So the DNN should not provide an instruction to go left if the intruder is approaching from the left, right? And this makes intuitive sense, and it makes sense for this to be one of your boundaries for the safe region, right? So no matter what you do, no matter what your exact behavior is for the ACAS system, right? If an intruder is coming from the left and you go towards him, right, then you can almost guarantee that that is a bad situation to be in. So it makes sense for you to try and at least prove that you'll not be in that horrible of a situation. Similarly, if the aircraft is flying low, it should not provide an instruction to go down because this will guarantee a crash, right? So what you can do is you can encode the bounds, such bounds of safe behavior, and then verify that your system always stays within this bound. So you can encode this as properties to be verified very formally, right? Because you can say that, if your sensor data is, say, if you have some sensor data that is basically the theta, which is the angle at which your intruder is approaching, right? And if you, let's say that if say your theta is positive, then that means it's left. The intruder is approaching from left. And then say that you have some phi, which is, or psi, which is the turn instruction. And again, if the psi is positive, then that means you're asking it to turn left. So you can say that, this should not happen. It should never happen that theta is positive and that, oops, okay. Yeah, and that psi is positive, right? So you can specify some, so you can take these safety bounds and more often than not, you can specify them very formally. So this is clear, right? No questions? Okay. Similarly, robustness is another thing that you can check very easily. See, again, neural networks are approximate. Small changes to input can have, affect an output. And this is actually something that is very well studied in terms of adversarial attacks. Like there are several methods in which you can design such small inputs that can affect an output, right? But this is often not a very desirable behavior, right? You often don't want some very small inputs to change an output, right? For example, there is this 1 pixel attack. So that is of course something that a face recognition system, it should not be vulnerable to a 1 pixel attack, because if your face recognition system is, for example, used in a lock in a bank somewhere, then that is definitely something that you won't be able to sleep well at night with, right? Similarly, for the ACAS XU system, a small momentary change in a few sensors should not cause the aircraft to send some wild instructions, right? in self-driving cars, lighting, rain, etc., they change the picture that is coming into the towards the DNN that identifies obstacles in the road. But of course, if these small changes in the input create a change in what a particular object on the road is identified as, then that can be catastrophic, right? So for example, if you have a red signal and suddenly because there is rain, the red signal is not seen, right? Or the car just ignores the red signal or ignores an obstacle, then that is very dangerous. So again, there are very well there is a very rich line of research that actually, given a certain network that has methods for creating such small changes in input, that will create a wild change in output. But what we are interested in is not just that, but can we actually prove that a network is immune to such things, right? Can we verify robustness? So what we want to do is verify robustness. Of course, getting a neural network that is actually robust is an entirely different problem, like I said, and maybe equally difficult. But what we are focused on is, okay, if somebody claims that this is a robust network, and we at least prove that, like formally, using some automated system. Yeah.
How would you encode robustness logically? Like
yeah.
mathematically?
So in terms of a logical query, you can encode robustness in this form. So for example, let's say that let's talk about changing only a few pixels, right? So you can say that you have your input I, which is a set of variables, and then you have some other I prime. So you say that I minus I prime is less than some very small epsilon, right? Or maybe you say that the I minus I prime differs only in some limited number of variables, which you can instantiate as a very large precondition involving all of the possible few changes that you could make. So then if this implies, say, if your neural network is n, if this implies that ni minus ni prime is greater than some delta, if you can find the I for which this holds, right, then you have found a counterexample to robustness, right?
It's not robust.
Yeah.
Then it won't be robust if you can find this.
Yeah. And of course, this notion of distance, it is, I mean, this mod over here, this has to be properly specified. So what exactly your mod is. For, let's say, if you want to check lightning, rain, and so on, then you could have some sophisticated mod that somehow puts a lightning filter or a rain filter on your image, right? So you can say that, okay, you take an image, you put a lightning filter on it, and you check that that filter is not very strong. It should not be that your signal is actually not visible at all, right?
Mm-hmm.
And then you apply neural network on both and check if the output is greater than delta. Mm-hmm. So these things can be formally specified via such queries. Those are at least, yeah.
If it is not robust, can you, like, how do you fix it? How do you make it more robust?
Yeah, so that is, as I said, an entirely different thing. So so from what I'm aware of, what you can do in most cases, that these adversarial attacks will give you some counterexamples to robustness. And they can also suggest changes that you can do to fix it. What is the other thing that you can do is, if you have some sort of test data and you trained on it, usually what people do when we're trying to train a robust network is, in any case, that they'll make sure that the input output in this test data set has a lot of clear images, a lot of rain images, a lot of cloud images, and so on, right? So it instantiates the various changes in input that the network should be robust to. But if you find another input that you're not robust to, then you can try and find a lot of such inputs, and you can add them to your data set and train again, right? So these are some things that you can do. And again, like you said, your question is again very good one, and there is probably a lot of potential there to properly do that in a very nice way. And that is a active field of research as well. Yeah. Yeah, so more places where neural networks, say, like checking neural networks makes sense. Security. So face recognition logs and voice recognition logs are a thing now, right? there should be a way to verify that neural networks don't behave in a way in such safety critical or security critical systems that violate security, right? So what happens is that oftentimes whenever some secure system gets hacked, it is because an exploit has been found that is a chain of vulnerabilities, right? So you have, say, you have your camera that feeds into your face recognition system, that feeds into, say, another set of some extra set of checks, maybe say an OTP check that feeds into, let's say, a deadbolt that finally opens your door, right? So you have this, most secure systems have this link of various security checks, and if you have to, or whenever these are get hacked, what happens is that some vulnerability is discovered in all of these, right? So you can, so someone figures out how to bypass all of these, and then they finally can hack the system. What happens more often and not, and that is, I mean, that is fairly obvious, is that so let's say that this is your camera, this is your network, this is your OTP system, this is your deadbolt, right? So what happens in most often than not, or more often than not, is that all of these vulnerabilities won't be found at the same time. Sometimes some of these are found in one of these pieces on this link or one of these links, and people actually get to know about that. These vulnerabilities are published, but oftentimes they're not entirely patched in all of the locks available on the market, or because they don't lead to immediately to a security exploit, right? So say if somebody has compromised one link in this, then you're not immediately hacked, but you're closer, right? So let's say that somebody compromises the another link. Let's say that somebody finds a vulnerability for the deadbolt, and both of these are now public. So again, you're closer. Finally, somebody finds a vulnerability for your, let's say, your some other OTP system, right? So now, if they can get across this neural network, the situation is that if they can hack the neural network, or if they can get the neural network to behave in some specific way, they have figured out everything else as to how to hack the system. So if we find ourselves in a situation like this, of course, the company who has the log, they are going to release a patch that is going to at least remove some of these vulnerabilities. But more often than not, what the procedure is that is to make sure that the patch, even if it inadvertently leaves this vulnerability in, right? Say they missed something, it should still not be possible to make the neural network itself behave in a way that you can complete this chain in some sense, right? So of course, for anybody to say that we have done this, or to say with some certainty that you can't hack this system because of this neural network, or this neural network won't, at least it won't lead to the system being hacked in this particular way, you need to specify, or you need to actually verify that, right? You need to prove that formally. So this leads to another potential source for verification problem, where this specific set of behavior that you have for the neural network, that this specific set of behavior is basically exactly that what will complete this chain. Maybe if you pass in a certain grainy input, certain grainy image, let's say, or noisy image, it should not lead to the network saying face, right? So it should not say that, the network should not say that I found this face, because if the networks does, then you figure out a way to pass that image via the camera, like bypass the camera to pass that image to the network, that specific image, and you figure out a way to bypass the OTP system that you would also have to go through. You figure out a way around the deadbolt, so then you have cracked the system, right? So this sort of a situation should be avoided. So again, this is a very specific and formal query, right? More often than not, it is a very specific set of things that you need to do to complete this chain, and you can specify that formally, and then you can prove that, okay, at least the network is safe against this, or secure against this, right? So that is another way, or another source and motivation of verifying safety for networks. Privacy. So another potential problem with DNNs is that sometimes they memorize the training data, and by memorize I mean exactly memorize. This is slightly different from overfitting, right? So okay, this is an aside. So people who are familiar with DNNs and training process, they might be familiar with something known as overfitting. If you're not, just ignore what I'm going to say. It's not relevant, very directly relevant for what we're talking. So overfitting happens when, you have a DNA that you've trained so much that it produces a low error for testing, but a high error for the actual real world, right? So I'm not saying that that is what's happening. Let's say that you have a training, or you have created a DNA that produces reasonably low error for testing and reasonably low error in the real world, but it still has memorized some training instances somehow, right? A good example of this happening was GitHub Copilot. So GitHub Copilot, I mean, I don't know if you guys are aware of this. It's basically a plugin for VS Code right now, is basically how it's being distributed, which is based on this GPT-3 system, which you'll basically give it some query in English, in plain English, and it will complete the code for you. So you can start out with a comment saying this is a function to do so and so, and then it'll write a code snippet for that function automatically. So GitHub Copilot is a GPT-3 based system which Microsoft has come up with as a plugin for VS Code. Is basically how it's available right now. You can, I think anyone can apply for trying it out, and people are getting it fairly easily as well. But the huge issue with this thing is that they're actually ending up memorizing several code snippets from many open and closed source projects that are hosted on GitHub, which is the training data that they use. They trained it on all projects on GitHub, and it's suddenly quoting these small code snippets from various different projects. And this is a legal nightmare, right? Because you're not always allowed to use these code snippets from various different projects. So this is another violation of privacy that can end up happening with DNNs. You would think that training a DNN with some data is essentially anonymizing that data, but apparently not. So if this is another thing that you would want a guarantee for, right? So if you're training some DNN with some privacy sensitive data, you would want to guarantee that your data has been anonymized by that DNN. The DNN won't actually spew out the data verbatim. Remember that the GitHub Copilot actually works very well in the real world. It's not like it's overfit, but it still memorizes some training samples.
They have solved the issue, or it's still currently working?
I'm not aware. As far as I'm aware, it's still there. Some of the this issue of memorizing code snippets is still there. And in any case, even if they were to claim that they have solved the issue, how do you verify that, right? Which is basically the question that we are working with.
Yeah, like because they have trained the data on the GitHub data set. So
yeah,
like that will be the issue, because like they have, if they would have taken open source data set only, then
even that is a legal issue, right? Because you might be working on a closed source project and your open source might be copyleft, for example, right? Just because it's open source, it doesn't mean that you can just freely copy from it. Yeah. So it is a big issue, and here's the problem, right? Even if they claim that we have fixed it, the only way to actually check that you have fixed it is via some formal verification, which is basically what we are saying over here. To produce a guarantee, we need to verify, right? Guarantee can only be produced via verification. And the GPT-3 system is like so huge, so that is, again, you'll have to somehow verify this entire system as to it's not memorizing this data, and that you can fairly easily put as a fairly heavy formal query, where you can say that you can take each point in your data and say that, okay, the network hasn't memorized it, so the DNN, or in this case it is actually a GPT, which is not exactly a vanilla DNN. It's got more aspects to it, but point is that it should not produce this Y, right? This should never happen. And you can put that as a formal query for each particular data point that you want to check for memorization, and then do that for all the data that you've trained with. Of course, it's not a great way, but right now this is the best way we have if you want an actual guarantee, which is what we are focusing on, right? Because if you have a guarantee, then your legal issues are like solved. You can just say that we have verified it. It will never memorize anything. Finally, we have some consistency. So consistency in terms of logical constraints. So your network, whatever environment it's operating in, it should violate or should respect the physical and logical constraints in that network, right? So for example, a network matching the photos of mothers with their children should not give you two matches for two mothers with very high probability for the same child, because that does not, that does not abide by physical laws or the logical constraints of your application. Similarly, the ACAS-XU system should not produce an instruction that the aircraft cannot follow, right? So for example, if it asks the aircraft to turn 90 degrees in 3 seconds, not all drones can do that. Nor can all drones just climb up all the way up to space to avoid a collision. So it cannot ever ask for such instructions. And at the same time, it should be safe, let's say. So that is basically what we mean by consistency. It should not ask, you should not produce outputs that make no sense. Another interesting consistency point of view or consistency problem that we can try and address that is sort of related is that GitHub Copilot, if we ask it to produce correct programs, that is kind of a consistency constraint, right? And by correct programs, we mean that programs that at least compile and don't have obvious bugs like division by error and such, which is again not guaranteed with the current GitHub Copilot thing, which is definitely not guaranteed right now. So that if you can do that, if you can like create a neural network which is guaranteed to be consistent with respect to program correctness, then you can imagine that this will be a very strong system, right? Yeah. So somebody says GitHub Copilot will take all of our jobs if it produces correct programs. Yeah. So that is a very a very clear existential fear, and I've thought about that for a lot. I'll not go into that because if I start talking about that, I'll end up talking for 2 hours. But I don't think that is the case. I think that it will take most of the jobs, but there'll always be some jobs left, which is again not a very optimistic picture, but it is what it is. What can you do? As computer scientists, our job is to make sure that we don't have job steady as well from now. Then that's how we do things. So yeah, especially in ML, I think. Yeah, but yeah, I think that's a very interesting discussion to have later on. Since we have only half an hour, I'll not go into that rabbit hole. Yeah, so any other questions at this point? Okay, so yeah,
So,
go on.
I had one question regarding security.
Yeah.
So like in the security slide, are there any examples of people exploiting neural networks in in systems? Like how would you
No.
go?
Yeah, so this to be honest, this is fairly speculative right now because there are I'm not aware of at least any vulnerabilities that have been that have exploited neural networks in some way. But definitely this has been a motivating factor for a lot of research, and as far as I'm aware, even for things like adversarial attack research, there has been some motivation from this angle, let's say. So yeah, I'm not, to answer your question, no, I'm not aware of anyone actually doing this, if that's what you're asking.
Okay.
Yeah, but I think it's a possibility is all I'm saying. So yeah, I think you'll agree that we have enough motivation to actually go ahead and spend some effort in trying to figure out how to verify neural networks, right? But that's not the only issue that we have in terms of challenges towards verification. Even if we have some property that we can specify that comes from any of these motivating angles, we still have the issue of scalability, right? So by the way, there were no other questions for the previous thing, right? Yeah, okay. Just stop me and ask even if you have some questions or something way back. Yeah, so in general, neural networks are complex. The DNNs are complex. And again, if we have time, we'll see a proof of this. But it's okay. How many of you are familiar with SAT? As in, what is, okay, I think something like 25% were familiar with SAT, if I remember the question here. Yeah, okay. So in general, a DNN is almost as complex as any logical circuit, right? So there is this, so a SAT query is basically where you have a bunch of variables, a Boolean variables, so variables that can either take true or false. and then you add a number of constraints on this variable. So let's say you say that v1 and v2 must be true, but then you say that v1 must be false, and then you say that not v2 also must be false. So these three constraints together cannot be satisfiable, right? So SAT query is basically something like this. So you take a number of variables, Boolean variables, and you create Boolean expressions in all of them, and you assert that, okay, all of these expressions that you've created must hold. And then you ask, is there some values for this variable so that such that all of these holds? So for example, if we didn't have the not v2, what we could have said is that, okay, yeah, it is possible that v1 and v2 is true and that not of v1 is true, right? You just set v1 to 0 and v2 to 1, right? So this SAT query is actually commonly understood to be a benchmark for complexity, because it is one of the things that we expect to be very hard to check, right? So right now, the only algorithms that we have for checking SAT queries are exponential time, right? So, okay, finally my network connection is unstable. Sorry about that. Yeah. So right now the only algorithms that we have for checking SAT queries are exponential in time, and there is an open conjecture that says that that SAT is actually the best you can do, the best possible algorithm that you can imagine to do a SAT check will always be exponential in size of the expressions that you put in, size and number of the expressions, right? So we use SAT as a sort of a benchmark for complexity. So if everything is, if checking something, some property is going to be as hard as checking SAT, then almost everyone agrees that it's fairly complicated to check that. So that is what I mean when saying when I say the DNNs are complex. And this is, again, if we have time, we'll see a proof of this. What we'll see is that you can actually encode a Boolean, a bunch of Boolean conditions, or let's say a Boolean circuit into a DNN, right? So you can take an arbitrary Boolean circuit with some ands and nots and so on, and you can actually encode it into a DNN, and then your Boolean circuit can represent a bunch of Boolean assertions that you have, and you can encode then your SAT query on these assertions as some sort of formal query on your DNN, right? So in some sense, if you can easily check queries on DNNs, you can easily check queries on SAT, because to check queries on SAT, then what you could do is convert it to a query on DNN, check it easily, and then convert it back, right? So you can easily go from SAT to DNN. So if this is easy, then that implies that this should be easy, correct? So essentially, since we can easily encode DNNs or encode SAT queries into DNN queries, and since we don't expect SAT queries to be easy, we don't expect DNN queries to be easy. So, but that really doesn't say as much, because although SAT queries we don't expect it to be easy, there are actually a bunch of SAT and SMT solvers and software verification tools that are actually very scalable and very good. They can handle, as sir said in the last tech lecture, they can handle upwards of 100,000 variables, which is amazing. But you see, that mostly comes from a lot of slow progress and methodical progress and a few let's say breakthroughs, but they're all with respect to software and in some cases hardware verification, right? They're not with respect to DNN verification. So there is a long history of progress for SAT and SMT solving, and DNN verification is relatively new. So we aren't at that stage yet where we have had some major breakthroughs and we can say that, okay, DNN verification is scalable. So that is some good research opportunity, and also some decent scalability challenge that we have right now. Okay, so one could say that fine, since we have good software verification tools, a DNN is at the end of the day a program, right? You can imagine a DNN to be a program that computes, or that basically simulates the DNN, let's say. Then why not encode a DNN into a program and then pass it to a software verification checker, right? This is actually not very efficient because what we're doing is you're going one level of abstraction lower than what you want to, right? You want to verify the DNN itself. This is what you want to verify. But what you're doing when you're doing this, what you're ending up verifying is you're also ending up verifying, let's say, the matrix multiplication engine that calculates your affine transform. Or let's say that you're also ending up verifying any loop that you have that loops over the number of layers that you have and such things, right? So there are some extra details that are coming in over here because you're one level of abstraction lower, right? And that leads to those extra details leads to extra variables and an increase in complexity. And what you end up seeing is that this approach of converting into a program is actually not very scalable at all. What is a slightly better approach is we can treat the DNN as a directed acyclic graph and then encode all of your various constraints into an SMT formula. So an SMT formula, like sir said in last time, is basically just a formula involving various variables and addition, subtraction, multiplication, division, and potentially first order, let's say, quantifications. But in this case, we can actually avoid those quantifications completely. So this will just be addition, subtraction, multiplication, division, and Boolean operators. So you can actually encode your DNN, the entire action of your DNN, into an SMT formula, and we'll show an example as to how to do that soon, like in the next few slides. But you see, this is actually yeah, so there are basically ways you can do this, and this is better, but scalability is still an issue, right? Because again, you see the SMT solvers that will eventually solve your SMT formula that you get over here, they are again, optimized via various heuristics, and those heuristics are again tuned for things like software verification, hardware verification, right? So what we really need, and which is what we'll see in later lectures in this course, is that we need dedicated SMT theories and solvers just for DNNs, right? So we need some sort of SMT solver that is designed from the scratch, from the beginning, ground up, just to solve DNNs. And there are actually solvers like this, an example being Reluplex. And we'll see many examples of this as we'll look at various papers towards the later half of this course, which actually try to do this exact thing. One of the good things about doing this specifically for DNN is that you can do some specific abstraction, which again, this will be explained in greater detail in the later part of this course, which is going to work specifically for DNNs. Yeah, so a lot of people left. So is that internet issues, or I guess there's no point asking you. Yeah. So like I was saying, you can convert a DNN into a program, which is what I've done over here. So let's talk about this. So any questions up until this point? Just give me a yes or a no.
No, everything clear so far.
Sure. Yeah. Right. So
no questions.
yeah. Okay. So let's look at a toy DNN and let's try to encode it into as a program, and then we'll try to encode it into an SMT formula. Yeah. So by the way, so this is supposed to end by 14:45, right? Or have I gotten the time wrong? 16:45, right?
Yeah, ideally it should end at 16.
Yeah, so I'll try to make that happen. I'll leave some of the details for next time, let's say. Yeah. So okay, so in another 4 or 5 minutes I will end. Yeah, I think that's why people left. So if you're watching this later on and you left, yeah, so okay. So in any case, so let's look at this toy example. So what we're doing over here is we have one input, one hidden layer, one output. The hidden layer has got 2 neurons, And what we're doing is we're taking this input value, multiplying it with 1, and then passing it to ReLU through ReLU to get the value of this neuron. And then similarly, we are taking this input 1, multiplying with -1 and passing it through ReLU to get the value here. And then we're multiplying both of them with 1 to get a final value at the output, which is this variable v31. So you can encode this entire thing as a program, right? So you can, so there's some pseudocode over here. So there, one input, which is going to be a real number, and there's going to be 3 outputs over here. So v21 is 1 times v11, but if that turns out to be less than or equal to 0, then we set v21 to be 0. So this basically calculates, in some sense, ReLU of. So this basically encodes this thing, right? That v21 is ReLU of 1 into v11. Similarly, this one will encode v22 is ReLU of 1 into v11. And then finally, v31 is just you multiply all of them with 1 and sum them and you return. So in this way, you can encode this as a program. But as you can see, there is a lot of extra things here. There's this if statement, which is a branch, which is extra. Most program solving tools will basically try to deal with this if statement in ways that are too not unnecessarily complicated for our applications, right? So instead, what we can do is we can encode it in terms of directly in terms of SMT formulas and then pass them, which is what we show in this slide. So what we do is we take one variable for each one of the nodes again, and then again we have a formula for each one of these, right? So we can say that we can have an equation defining each variable. So we can say that v21 is 1 times v11 if that is greater than 0, otherwise it's 0. Similarly for v22, and similarly we can say that v31 is just going to be the sum of v21 and v22 times 1, right? So now for various queries that we want to do with this network, what we can do is we can also add, get extra conjunctions for each one of these queries. So or extra constraints for each one of these queries and add them as conjunctions and pass it to SMT solver. So to the SMT solvers, we pass these 3 constraints, right? So this fix the values of v21, v22, v31 with respect to your input. And then when we also say that, okay, we'll pass another set of constraints that represent the various properties we want to check. So for example, if you want to check this property, whether v11 is always equal to v31, right? So then we can pass these 3 things. And additionally, we can also pass a property that looks like this, right? Similarly, if you wanted to check whether spoilers, but this is actually not true. But if you wanted to check something like if v11 is equal to v31, but only for non-negative inputs. So we're restricting to the case where inputs are non-negative, right? So then what we could do is we can say that the precondition is this and the post condition is this, and then we could pass a property something like this, right? So we can say that v11 is actually non-negative and v11 is not equal to v31, right? So if we pass this and all 3 of these to an SMT solver and it says that, okay, this is actually satisfiable, then you have found a counterexample to your property, right? You have found an input which is non-negative for which the equality that you wanted to check does not hold. So similarly, you can do this for other possible inputs as well. So yeah, so this is all that I wanted to cover right now. So I have another slide on this, some SMT-lib2 syntax for passing to an SMT solver, but I think we can do this later on separately. Yeah, thanks for sticking around a bit longer.
I have a question.
Yeah.
So is it possible, instead of doing all this, can we just convert the neural network into some other because of the universal approximation theorem, can we convert this into some other machine learning thing like SVM and then do verification on that?
Yeah, that's actually a great idea. But again, the problem is when you do this conversion into an SVM, there will be some tolerance involved there, right? So the universal approximation theorem talks about only approximations.
Okay.
So of course, what you could do is, if you have some property that you want to check, if you can convert it to an SVM, and show that, okay, the tolerance which we get when we convert it to an SVM is good enough for showing this property, right? Then that is actually a great approach, and that is potentially a great abstraction approach for checking neural networks. But of course, there's two problems here. One is to actually show that this conversion holds with your given epsilon, and to show that, you know, finally that the SVM that you have to do the verification on that SVM itself, right? But yeah, I think this is a great idea. You can in fact think about this, and
So like, is verification on like SVM or other things easier than neural networks?
Well, for SVMs, I think will definitely be easier than DNNs, but I think for most complicated case, this step one is going to be fairly difficult, right?
Yeah. Or maybe you could, like, in production, use that SVM instead of neural networks.
I mean, yeah, you could in production use something simple that will always reduce your chances for bugs. But I mean, if you could do that, then people would have, right? People use DNNs not because they want to use DNNs, but because they get the job done better than any other things, right?
Yeah.
So it might not be possible to use an SVM for an ACAS XU system, for example.
True.
If it was, they would have, right? If it was reasonable or efficient to use that.
Yeah.
Yeah. So any other questions? Okay. So yeah, so if there are no other questions, then yeah, so I guess we'll end this meeting now.
Yeah.
I'll stop this sharing. I'll